Okay, we'll go ahead and get started. Can everyone see my screen and hear me okay?
Yes.
Thank you. So what we're going to do today is we'll start off by beginning chapter 8, where we'll talk about chemical bonding. And then at about 11:30, I'll stop, and then you guys can take the quiz. One comment about the quiz: there are some questions where you have to write out reactions, and so if you can't find an arrow key, just go ahead and use the equal key to have the reactants equal whatever the products are. Okay. All right. So in lab, you started talking a little bit about bonding and Lewis structures and things like that. So we're going to start some of that discussion in class. So hopefully some of this will be familiar to you from what we did in lab. When we talk about chemical bonds, what we're talking about is two atoms or ions that are held together. And there's three basic types of bonds. There's ionic, covalent, and metallic. With ionic bonds, you're talking about an electrostatic attraction between oppositely charged ions. So ionic bonds are typically, you have a metal and a non-metal, and the metals, we talked about how those ions are usually cations, and metals like to donate electrons, and non-metals are typically anions, and they like to receive electrons. So in the ionic type compounds, it's that electrostatic attraction that keeps it together. So in other words, the opposites attract thing that we've been talking about. Covalent bonds, in that case, the atoms are sharing electrons. So there's not a donation or an acceptance of electrons, it's a sharing of electrons. Now we'll see a little later that sometimes the sharing is equal, sometimes it's more towards one of the atoms than the others, and we have some terms that we'll talk about that describe those situations. But covalent means you're sharing electrons between the atoms. And covalent bonds are by far the most common type of bond that you see. I've mentioned organic chemistry is a type of chemistry that's studied, and that's compounds that contain carbon. That's all covalent bonding for the most part. And then the third one, which is the least common, is metallic. And that's where with metals, you have the free electrons around the metals holding metal atoms together. We won't talk much about that. We'll talk some about ionic today, and going forward, we'll focus even more on the covalent bonds. So we touched on this a little bit in the last lab, and that's the Lewis dot structures. And so Lewis developed this method to kind of denote the bonding electrons by using a dot for representing a valence electron and putting it around the element symbol. And so when we form compounds, atoms can gain, lose, share electrons, and Lewis devised this way of where you want that you want that element surrounded by 8 valence electrons, and this is known as the octet rule. So down at the bottom of the slide here, we see cut out from the periodic table. And what we see is on top, we see the group number. So remember, that's the columns, 1A, 2A, 3A, 4A, all the way up to 8A. And then we see an element listed, and then the electron configuration. And then finally, what would be the Lewis symbol for that element. And what you see is, you see a dot next to the element. and that dot represents a valence electron. The other thing you should note is as you go across, you see lithium has 1 dot, beryllium 2, boron 3, carbon 4, on down the line, all the way to neon at 8. What you should notice is that the number of dots, or the number of those valence electrons, is the same as the group number. So in other words, all the elements in 1A have 1 valence electron, 2A have 2, 3A 3, on down the line. So when you go to do these Lewis structures that we'll be talking about in a little bit, when you go to draw those dot structures, what you want to do is you want to look at the periodic table and see which group it's in, which column the element is in. And that will tell you how many dots, how many valence electrons go with that element. Let's talk a little bit about ionic bonding. So ionic bonding, as we mentioned, means you have a metal and a non-metal involved, and there's an electron transfer. So we've talked before about how metals like to donate electrons. So in other words, they like to be positively charged, which means they lose electrons. So they like to donate electrons. The non-metals like to be negatively charged, so they like to accept or pick up electrons. We're not going to, this doesn't really apply to group 8A, that's the noble gases. Remember, we talked about the noble gases are fairly inert. So you don't get a lot of reactions involving those. So this electron transfer occurs between the metal atom and the non-metal atom. And this process tends to be very exothermic. Remember, exothermic means it's giving off heat, it's giving off energy. So if we think back to last chapter, we talked about ionization energies and electron affinities. So to show how that thinking fits into, and that terminology fits into this ionic bonding, that element that gives up the electron, so in other words, the metal, that element has a low ionization energy. So since it's a low ionization energy, it's easy for it to lose an electron. We don't have to put a lot of energy in there for that electron to be donated. The element that gains the electron, the non-metal, we would say that that has a high electron affinity. So in other words, low ionization energy on the metal allows it to form a cation and then donate that electron to the non-metal, which has a high electron affinity. So it has a high interest in gaining that electron. So down below, we see what happens with sodium and chloride. So we have that 1 valence electron on sodium. That electron moves over to the chlorine, and the chlorine now has a full octet. We see the 8 dots around it for the 8 valence electrons. And we draw that with those 8 dots, and then we put a parentheses around the chlorine, and then a minus around as a superscript to indicate that it's picked up an electron. The sodium doesn't have any more dots around it because all the valence electrons are gone. The 1 valence electron it had has been donated over to the chlorine. So that has a positive charge to it to indicate that it's lost an electron. When we think of the ionic substances, there's a few things that are common. And one is that it has a well-defined three-dimensional structure. And you see a picture here of sodium chloride, and this kind of well-organized pattern type structure is pretty common for these ionic compounds. The other thing is that these substances tend to be brittle, and they have high melting points, and they're crystalline. And so there's people who do study things called crystal structures, and so that's where they study to see how these arrangements are. They also tend to cleave across some of the smooth lines that you see here. So that's some of the properties of ionic substances. We'll see in a bit that covalent type compounds are very different in these properties. So let's talk about some of the energy involved in ionic bonding, something called the Born-Haber cycle. And so there's a lot of factors that affect that total energy in ionic bonding. So if we use the sodium chloride as an example, and we start with sodium, solid sodium, and then chlorine gas, we first have to make the gaseous atoms. So we have to convert that sodium solid to sodium gas, and we have to convert Cl2 to Cl gas, just the atom chlorine. Then we need to make ions. We need to make sodium plus ion and the chloride minus ion. And then that needs to be combined. And so we see an energy diagram over there on the right showing the different steps and showing the energy that takes place. Let's take a look at that a little more closely in terms of what's going on. So it takes energy to convert elements to atoms. So that first step where we're converting, going back here, converting the sodium and the chlorine gas to the atoms, that requires energy. So that's an endothermic process. Then in order to create the cation, that requires energy because we're trying to remove those electrons. That's endothermic. Forming the anion, where you're accepting an electron, that's exothermic. So we've got a couple of endothermic steps, we've got an exothermic step, but then the final one, going back once again to this picture, where we actually combine the sodium ion and the chloride ion, that's over there on the right with the red arrows, we see a big exotherm with that. And that final making of the ionic compound, in this case sodium chloride, that's a very large amount of energy involved, and it's exothermic, so it's giving heat out, giving heat off. So in general, formation of these kind of ionic salts tend to be exothermic because of kind of the stepwise fashion that we just discussed. When we talk about ionic compounds, there's something called lattice energy, and I'd like to talk about that a bit. And so the reason why the ionic compounds are stable is that there's an attraction between the ions of opposite charge. So you go through this process, and now you've gotten, in our last example, the sodium, which is going to be positively charged because it's donating an electron to the chlorine, and then the chloride ion has picked up that electron, so it's going to be negatively charged. So it's that opposites attract type approach that we've talked about that keeps the compound together. So the energy that's required to completely separate, if you have 1 mole of material, to separate it into its gaseous ions, in other words, break apart that solid, that's called the lattice energy. And down below, we have an example of that for the sodium chloride. So if you have sodium chloride solid and you put enough energy in, you can break it apart into sodium plus gas atoms and chlorine minus gas atoms. And in this case, that lattice energy is plus 788 kilojoules per mole. It's plus because we had to put energy into it. If we go the other way and say we had that sodium cation and chlorine anion, chloride anion gaseous form, and we were combining that to make the sodium chloride solid, then that would still be 788 kilojoules, but it would be a negative value. Because if you're going that other way of forming, we just said that that's a real exothermic process, so the sign would change. Here's some examples of lattice energies for different compounds. The higher the number for the lattice energy, the more stable the compound, the harder it is to break it apart. So in other words, you'd have to put a lot more energy in some of these, let's say magnesium chloride, than you would for cesium chloride. When we think about lattice energies, there's a couple trends that are important. One is that the lattice energy increases as we increase the charge on the ions. And so what that means is if your ions are, say, +2 and -2, that's going to take more energy to break that apart than if the ion charges were +1 and -1. The lattice energy also increases as you decrease the size of the ions. So if the ions are smaller, then it takes more energy to break that apart as well. So once again, lattice energy increases with increasing the charge on the ions, and it also increases as you decrease the size of the ions. There's a formula down here which can be used to do some lattice energy type calculations. And you see that it's based on a constant and also the charges of the particles, and then the distance, between the centers. So we're not going to worry too much about this exact calculation. Should be aware of it. But what you should be more aware of is that lattice energy increases with the charge on the ions and decreases with the size. Decreasing size of the ions also increases it. So there are a couple of homework problems I'd like to go over here for a bit, just to make sure everyone is on the same page with this. So the first one is 813, and it asks you to write the Lewis symbol for the atoms of a couple of them. And we have a aluminum, bromine, argon, strontium. And so what you would do for this, as we said, is you'd write down the symbol for the element, and then you would go to the periodic table to see which group they were in. And the group tells us how many of those valence electrons are there. So that tells us how many of the dots are there. So aluminum is in the 3A group. So they would have 3, bromine 7A, argon 8A, strontium 2A. So that's why we would write the number of dots around the element symbol. So that's pretty straightforward, as long as you remember to go and check the periodic table to see what group it's in. The next one I'd like to talk about a little bit is 815. So here they asked to use the Lewis dot structures and diagram the reaction between magnesium and oxygen atoms to give magnesium oxide. So once again, we'd write the element symbols, in this case Mg and O, and then we would look to see what group they were in on the periodic table. You see the magnesium is 2, so it's in the 2A group. So we have 2 dots for that. And then oxygen is in the 6A group, so it has 6 dots around it for the 6 valence electrons. As we discussed in this ionic bonding type situation, the metal's going to donate electrons. And so we shift those 2 electrons from magnesium over to the oxygen. And that completes the octet for the oxygen. So now we have 8 dots around it representing 8 valence electrons. So the magnesium is lost 2, so we need to put a +2 superscript for that. And then the oxygen, we go ahead, fill in the 8 dots, put the parentheses around it, and give it a -2 superscript to indicate that it's picked up 2 electrons. So in this case, in this reaction, this electron transfer reaction, we have 2 electrons moving from magnesium to oxygen. So this kind of stuff, I think, is pretty straightforward. As I said before, the key is remembering to use that periodic table and the group, looking at the group designation for the element you're interested in. That tells you how many of these dots or valence electrons should be present. Okay, let's look at 819. We're going to write the electron configuration for these ions. And so what we want to do first is we want to write the electron configuration for the element itself. So for strontium, for instance, we see that we have our noble gas core and core electrons represented, and then we have 5s2. So we have 2s electrons that are the valence electrons. When we then write the Sr plus 2, we remove those 2 electrons, those 2 valence electrons, and now we're left with just our noble gas core. For Ti, we have, once again, we write our noble gas core, and then we have 4s2, 3d2. What you'll see here, though, when we lose 2 electrons, so we lose 2 because it's a +2 ion, we don't lose them from the 3D, we lose them from the highest quantum number. In this case, that's the 4s. And so now we have just the 3D2. So this doesn't get us to a noble gas type configuration. The next one, selenium. Once again, we write that noble gas core. Then we have 4s2, 3d10, 4p4. The selenium, we're saying, is picking up 2 electrons, and we know that because there's a -2 charge involved. And so by adding 2 electrons, we add them to that 4p orbital. So now instead of having 4p4, we have 4p6 that fills that orbital, and that 4s2, 3d10, 4p6, that is equal to the next noble gas. So by adding those 2 electrons, we do attain a noble gas configuration. And then the last one we'll look at is nickel. And so we write the nickel electron configuration out, and we see those valence electrons are 4s2, 3d8. It's a +2 ion that we're interested in. So just as we saw up above, we're going to lose the 2 electrons from the highest quantum number. In this case, it's the 4 and the 4s2. So we lose those 2 electrons from there and leaves us with 3d8. Any questions on any of that? Okay, we'll move on and we'll talk a little bit more about electron configurations of ions. So we did some examples of this just now, and the metals lose electrons, and that often results in the electron configuration of the previous noble gas. The nonmetals can gain electrons, and that can result in electron configuration going to the nearest noble gas. So it makes sense because by adding a couple or losing a couple of electrons, if you can get to that noble gas configuration, that's a real stable configuration. And you think about it, we're always trying to achieve a stable configuration, lowest energy, things like that. Now, if you go back to our table here, I'm just going to scroll back for a second. We started talking about this. Something you should note is we didn't really mention the transition metals. Okay, so that's the B series of groups, kind of the dip down when we look at the overall periodic table. So we were focusing on just these 1A groups, 2A, the other A groups. And the reason for that is the transition metals do not follow the octet rule. So the octet rule works great for the things that we talked about, those A group elements, but when we get to the transition metals, it doesn't follow the octet rules. The transition metals also lose valence electrons first, then lose the d electrons necessary for a given ion charge. So lose valence electrons first, then start losing d electrons. I had mentioned before that covalent bonds are the most predominant types of bonds that you encounter. And so let's talk about them a little bit. So in that covalent bond, different from the ionic bond, in that covalent bond, you're sharing electrons. And so there's several things that are at work in terms of the electrostatic interactions in this type of bond. So we have attraction between electrons and nuclei. So that's that negative, positive, opposites attract thing. We also have repulsion, what we call electron repulsion between the electrons. So there you have all that negative charge kind of pushing off on each other. And then we have repulsions between the nuclei. So the nuclei are positively charged, but they'll have that same repulsion as we talk about with the electrons because their charges are the same. So in order for a bond to form, those attractions must be greater than the repulsions. And so there's always kind of this competition between the attractions versus the repulsions to see which is going to be the stronger force. One thing I want to point out to you is if we look at the figures on the right-hand side of the slide, the B figure in particular, we see two nuclei, that's the plus marks, and then we see similar to what we saw in some lab stuff of where we see all these blue dots around. And the blue dots are representing the probability of electrons being there and all that fun stuff that we learned in lab. For what we'll see though is for the electron density is the greatest in between, like if we drew a line from the one plus to the other, it's in between there. And so that concentration of electron density, where it's the highest, that is the covalent bond. So that's where the bond is occurring. And that's what's represented by that greater electron density. That represents the bonding between the two atoms. So when we draw our Lewis structures, we can show the covalent bond by a line. So like here you see two examples. So we could either have a line like between the HH or between the CL, or we could have two dots there. Either one is the same thing. And so you see on the chlorine, we have 6 other dots on each of those because that fills out its octet. Hydrogen doesn't have any more electrons, so there's nothing else to do on that. So we're going to talk more about these Lewis structures. We'll talk about some bonding in terms of double bonds, triple bonds, things like that, and how that factors in. But for right now, I'm going to stop so that you can start the quiz. So just a reminder, when you get to the part on the quiz where there is a reaction to do, if you don't have an arrow key or anything, just use equal sign to separate the reactants from the products. So are there any questions about anything before we start the quiz? Okay, then go ahead and pull the quiz up and start on that, and good luck on the quiz. Thank you.